My name is Chris Ward. I did number 47 from chapter 16 from the very first assessment. I modified some of it. I changed the value of A, the value of B, and I added a third charge at C with the vector point. We're at, kind of in between A and B, where A is 1 meter from the top, B is 1 meter to the right, and how they're acting on force D, or point D, and C is halfway. I also changed the charges, whereas in the book they were 1 nanocoulomb each. I changed it to make it a little bit more interesting. First thing I did was find the basic vectors. Vector A is at 0, -1, 0 from A to D. Vector B is -1, 0, 0 from B to point D. These are in meters. Vector C is at -5, -5 from C to D, or C to D. That's also in meters. The magnitude of vector A is just 1. Magnitude of vector B is also 1. Magnitude of vector C is 0.707, or square root of 2 over 2, or I'm going to use 1 over square root of 2. Unit vector. Vector A is 0, -1, 0. Vector or unit vector for vector B is -1, 0, 0. Unit vector for vector C is -0.5 over 1 over 2, or 1 over square root of 2, -0.5 over 1 over square root of 2, where it comes out to -5, -0.5 times the square root of 2, -0.5 times the square root of 2, 0. And then the total electrical field is just going to be all 3 of these added together. So take my K value, multiply it by the charge at point A, divide by its magnitude, which is just 1, and multiply by its vector, which gives its vector, where it has a 0, -9, 0 newtons per coulomb. I did the same thing for B, which 5 times 10 to the -9, which gives -45, 0, newtons per coulomb. And then C, same for these 2 vectors, which gave 38.2 newtons per coulomb. And then the final vector is just for D, just all of them added together. So final total was netted 6.8, 29.2 newtons per coulomb, 0 in the Z direction.